We'll be looking at material balance. Well, we'll be looking at fundamentals of material balances, and then probably you can solve some 2 or 3 questions. Now, so the whole idea of chemical engineering involves a processing of raw materials into um, finished products or valuable products. Now, there are two main processes we chemical engineers deal with, and that's batch process and then continuous process. So these are the batch process and then the continuous process. Now, when you are looking at how the processes varies with time, then we can talk about batch process and then continuous process. And also, when you are looking at the process as a whole and how it's being built, then we can look at three main processes: semi-batch process, steady state, and then transient process. I think as time goes on, we'll get more information about that. Let me just talk a bit about this too. Now, with the batch process, just take it as um it's a process in which there is no material input and a material output. You feed all your input at once and then you close your system. And after some time, you open it. I don't know if you so a typical example would be like the way we operate our rice cookers. We put in our water, we put in our rice, put in our oil, salt and everything. And after we close it, then after some time, we come and open to see the product. So that's how batch systems operate. But then with a continuous process, we are always putting in something and then we are collecting something out. Just like the corn mill. If you've been to the corn mill before, they're always putting in the maize and some is coming out. It's a continuous process. So that's the two main processes we'll be looking at today. So based on how the processes operate, we have semi-batch, steady state, and then the transient. I think I spoke much about them on this slide. So the steady state process, when we talk about steady state, we are trying to say that the process variables, which are our temperature, pressure, volume, our flow rate, which is our volumetric flow rate, mass flow rate, molar flow rate, do not change with time. So anytime you're operating a process and then there are conditions are that our process variables do not change with time, then you should know that we are talking about steady state processes. And for that process, our accumulation is zero. I think by now you guys wouldn't understand the accumulation part, so I'll just leave it for as we go on. And then for the unsteady state processes, the process variables change with time. So as you are operating, so let's say if you have a reactor which is operating under steady state condition, another name for the unsteady state condition is the transient state. So anytime you have a reactor which is operating under unsteady state condition, then it means that the temperature changes as time goes on. So let's say after every 30 minutes or let's say after every 5 seconds, there is change in temperature or is change in pressure. But then for the steady state processes, the variables do not change. The process variables do not change. And the flow rate also do not change with time. Now I've already spoken about this batch processes and I also spoke about the continuous process. Now with a continuous process, we can choose it to operate at a steady state or unsteady, whether we want the process variables to change with time or not. Right. So when you have your continuous process actually determine if your continuous process is going to operate under a steady state condition or unsteady state. There are two main processes, right? And then the process no material inflow and the material outflow in the sense that so let's say when you have a reactor which is operating under a batch process, right? Or let's say if when you have a reactor which is a batch reactor, the idea is that we just put in all our inputs or all our feed, and then after some time, like an hour, then we go and then open it to see our product. A typical example is how we operate our rice cookers. We put in our rice, water, and everything. Then after some time, we go and check our product. That's how the batch process operates. Now with the continuous process, like the name goes, there's always inflow and then there's always outflow. Right? A typical example is the corn mill. When you go to the corn mill, realize that they're always putting in the maize and then some is also coming out. It's a continuous process. And then when the batch one, you put in everything at once. After some time, so like you put in everything, you close it. After some time, you go and then open it. Right? And this one, I'm talking about how the process is being built. And I'm saying we can operate these two, both the batch and the continuous. We can try to operate them as a steady state, transient, or semi batch. Now with a steady state, when you're operating a continuous process under a steady state condition, what you are trying to say is that our process variables do not change with time. So our temperature, our pressure, our volume or our flow rate do not change with time. They are always the same throughout the process. So if let's say I have a reactor and then the reactor is operating under a steady state condition, then it means the temperature of my reactor input will always be the same. It wouldn't change as time goes on. And then for the unsteady state process, with that one, the process variables change with time. So as time goes on, you realize that there is either increase or decrease in your temperature, or if it is pressure, or if it is your fluid. Now, so this part, I was saying that the batch process is on its own. It tries to determine that whether what or the process that we are doing, we are continuously putting in feed and then continuously taking out products. But then with the batch process, it's telling us that we just feed everything at a go. And then after a scan, you can either operate the batch process as a steady state process or unsteady state. So with these two, this steady state and then the unsteady state, it's like something on their own. They are trying entire process as a whole, or the input and then the output. Please are we okay? So you can either operate our batch process as or unsteady state. The same applies to our or unsteady state. We feed in the um our raw materials, we feed in our raw materials, and then we continuously remove products from it, which operates between both the batch and then the continuous process. But then it's somehow complicated for semi-batch. That's why I was saying that the two main processes we look out are the batch process and then the continuous process. Now, because we'll be doing material balance, we first have to know our process, whether you're operating under a continuous process or a batch process. And then we should also know whether we are operating under steady state condition or unsteady state condition. And this will help us perform our balances. When it comes to the balances, there are two main types of the balance. We have the differential mass balance and then we have the integral mass balance. Now the differential mass balance is typically applied to continuous steady state processes. But then for the integral, it's typically applied to batch processes. Because in that one, there's no continuous input and output. So we are just like just take it as if we are integrating the thing from time t equals zero, where we start the process till when we finish the process. Because mind you, with the batch process, we feed in everything and then after some time we go and check. So the balance we do on batch processes, we call it an integral balance. And then for the continuous process, it's called a differential mass balance. Now when we talk about a system is anything under discussion or something we are looking at or anything under analysis. So if probably we are looking at a reactor, then our reactor becomes our system. Right? So we have types of system. The system could either be a closed system. This the system could either be a closed system. So with a closed system, there is no exchange of material. So closed system, also known as a batch system. When you look at it, we just the system is being closed. We can't exchange material or matter within the system because, of course, you've closed the thing, so we can't put in any other thing again. And then we can't take any other thing out from the system again. So the closed system is also known as a batch system. But then we can have changes in energy within the system. And then we also have the open system. So you can take the open system as a continuous process or a continuous system. So that one, there is continuous exchange of material within the system. We are feeding in and we are taking out continuously. And at the same time, the change. So the whole idea of the material balance, we are accounting for the material input and then output. So if you have any system and then we are putting in like 10 kilograms of, let's say, salt, but then only 8 kilograms is coming out, then we want to account for where that 2 kilograms has passed. That's the whole idea of material balance. So with the total balance or the general balance based on the conservation of mass, the general equation for material balance is our material input to the system, what you're actually putting in into the system, plus what is being generated within the system. So let's see if in a reaction, maybe you put in sulfur, you put in another compound. When you feed this into the system, new compounds are being formed. That's why you are calling acid generation. Right. So our material input to the system, then our material, when I subtract or let's say minus our material output from the system, what comes out from the system minus material consumption within the system. Because you know for any reaction to take place, there should be breaking of bonds. Some compounds should be consumed for other compounds to be formed. Right. So the general mass balance equation is material input to the system plus material generated within the system minus material output from the system minus material consumption within the system should be equal to the accumulation or how much which has been accumulated within the system. So let's say I input 20 kg of, let's say, salt, and then um let's say 5 kg of sodium is being produced, or let's say it's being formed within the system. So here I'm getting like 25 kg. Now when 10 is coming out from the system, so let's say 10 kilogram of salt comes out from the system, then it means I'm left with 15. Now the material being consumed here, I fed in 20 kilogram of salt. Let's see if 8 kilograms of the salt was consumed to produce the product that I want. So minus the 8. So 50 minus 8 giving us 7. That 7 means that 7 should be equal to the amount of salt or the amount of both the input, the salt I placed in, and then let's say the sodium which was generated, the amount which has been accumulated in the system. So when I open my reactor, I'm supposed or I'm expecting to see 8 kilograms of both the salt and then let's say the sodium present in the reactor. We are looking at the general or the overall material balance equation. And the equation is material input to a system plus the material generated in the system, E. And then we are expecting to produce material B. Now when I put in there 20 kg of material E and say 5 kg of material B is being formed in the reactor. Within that reactor, I now have 25 kg of material in total. And let's say 10 kilogram of the materials came out. That is both the A and B. When I sum them together, 10 kilogram is coming out. Then it means that now in the system, I have 25 minus 10 kg, giving me 15 kg, right? And let's say within that system, out of the 20 kg of material A that I placed in the system, 8 of them, 8 kg was consumed, produced the product B. Because if there's any reaction going to take place, some bonds need to be broken for other bonds to form, right? So that is the generation and then the consumption I'm talking about here. So let's say if 8 kilograms of material A was consumed within the reactor, then I have to subtract that 8 from the 15 I have, and then I'll be left with 7 kilograms. So that 7 kilogram actually represents the amount of both the A and B which is accumulated in the system. Just take it as if, let's say your mom sends you money, right? And then your mom sends like 20 CDs to you. And then you're able to withdraw, let's say, 8 CDs. So you're left with 12 CDs, which will be on your phone. So that 12 cedis left on your phone is what you are calling as amount accumulated. And then your material input is the amount your mom sent to you. And what you draw is the amount coming out. This is the general mass balance. So for every system, this one holds. There are some systems that some of the terms might go to zero. Right? But then in general, this is a material balance equation in general. Now, when you are going to perform the material balance in a continuous process, which is operating under a steady state condition. Now, we said that with a steady state condition, we gave, we said for the steady state, accumulation is zero, right? Good. And then you're operating at a continuous process. So you're looking at a continuous. So a continuous process, there will always be a material input. So the continuous process operating under a steady state condition. So there is no accumulation of material within the system. So this part goes to zero. Input because it's a continuous process. And then there's always material out on the system you are looking at. And there might be material consumption. So we end up getting material input plus material generated within the system should be equal to material output from the system plus material consumed. So for a continuous operating at steady state condition, it has no accumulation. So the moment you hear a steady state condition, a steady state process, just note that this accumulation part. Now, when you are writing the material balance for a general or overall material balance, so everything is inside, whether there is reaction or not. But then when you are looking at a system where there is no reaction, then there wouldn't be any material generation, and then there wouldn't be any material consumption. Um, you can take the corn mill for instance. When you put in the maize and then you are just milling the maize, this is not a reaction. So we expect that no other material will be generated, right? And then the material you fed in the corn mill wouldn't be consumed to produce a different product, right? So we end up getting the generation term and then the consumption term being equal to zero, right? This is for non-reactive systems. For non-reactive system, there's no reaction taking place. So you just have your input equal to output, provided you are operating under a continuous process, right? Where there is no accumulation. So what you have to know is you have to know this overall material balance equation. So depending on so you can make adjustment. So if you are dealing with a continuous process, then you know your accumulation is zero. If it is a non-reactive system, your material generation part goes to zero. Your material consumption part goes to zero. So you are left with material input minus material output should be equal to zero. And that will give you input equals output. So what you feed in should be equal to what comes out if there is no accumulation and if there is no reaction taking place. Now, procedure for solving material balance problems. In material balance problem, you will usually be given a description of a process. So it's always in a word problem form. The values of several process variables, a list of quantities to be determined in order to solve a material problem. So they always give you the question in the problem form, and you have to extract the important information you need before you can start performing your material balance. So these are some of the guidelines you should take note of. You first have to draw and label the process flow diagram. You just have to do a sketch of what the process or the system is talking about. Mind you, if you get the sketch wrong, that means everything will be wrong. So the very first step is very, very important. Make sure you're able to draw the diagram or describe or draw the process the question is describing well before you can proceed to the next step. The second one is to identify all your input and your output streams and label them correctly. So you should know. The next step is write the values of known stream variables and assign as symbols to unknown stream variables. So the streams that you do not know the actual values, make sure you assign variables to them and make sure that the variables you are assigning to them are different from other ones. You should assign unique variables to them, right? So that you don't get confused. The next step is to select a basis for your calculation. I think yesterday we spoke about how to set a basis. Now, for material balance, we set basis mostly for your feed input, right? So if they don't give you the amount of feed entering into the system, you can set a basis for that. You select a basis for that, and that wouldn't change your final answer that much. The fifth step is you now write your material balance equation, and then you can start solving. But then you have to start solving with the ones or the equations with very few unknowns. And the 6 and 7, we'll talk about that one later. So you have to choose the equation with the fewest unknowns, because some of the equations you might need other variables, but then you wouldn't know them. You have to start. So if you have an equation that has just one unknown, you try and find that one first before you proceed to the next one. Use the total balance equation as soon as possible. Right. When you start solving questions, I hope you guys will understand this part well. So when you are setting up your balance, you have to make sure that the total balance equation, you go for that equation first before you try other ones. This doesn't work for all questions or for all, problems. But then ideally, that's what you're supposed to do. And we also talk about process flow diagrams and then flow chart. Because the question will be given to you in the description form, you have to be able to extract the data. An amount of 100 kg per hour of a mixture of 50% A and 50% B. So now, I I hope by now we know what 50% A means and what 50% B means. So our 50% A and our 50% B here is giving us idea on the mass fractions, because this is a mass flow rate here. So it means that the mass fraction of A is 0.5, and then the mass percent is 50%, and that for B is also 50%. Now, because this we've been given our total mass flow rate here, so it means that the mass flow rate of A will rather be 50 kilogram per hour, not 50 grams. And then the mass rate of B is also 50 kilogram per hour. So we have this separated in a distillating column. The distillate contains 90% A, and the bottom stream composition is 95% B. And please, when you talk about distillation column, how many output should it get? We said that for a distillation process or for a distillation column, because it's a separation technique, we have a feed create them. So when you separate them, you're going to get an upstream and then a downstream. That is a distillate and then the bottoms. And that means that we say, but then the separation wouldn't be 100% efficient. So even out of the upstream that we are getting, you might get some of the components still present in it. And then for the bottom stream, for a distillation process, you are getting two outputs. That's for simple distillation. So the distillate contains 90% A. When you talk about distillate, that's talk about components. You can have just one stream, but then that stream consists of more than one component. It doesn't mean there are two different streams. So it's a mixture. So the distillate itself is just one stream that's coming out, but then it can consist of two or more components, A, B, and C, all present in that stream. And then the bottom is also another stream, but then it can also consist of more than one component. So A, B, and C all together, but then it's coming out as just one stream. So for a distillation column, you get one input and you get two outputs. So let's see how to draw it. Now the first statement is an amount of 100 kg per hour of a mixture of 50% A and 50% B is separated in a distillation column. So we first have our distillation column, and then we can put in our feed. Right? So this was entering the distillation column. And then the question says consists of 50% A. But then before that, we should know the distillation column should have two outputs, right? So this our feed entering and then our two outputs. Our feed consists of they give amount of 100 kg per hour of a mixture, right? So that is our feed, 100 kg per hour. So this is our feed. And then our feed consists of 50. So an amount of 100 kg per hour of a mixture of 50% A and 50% B is separated in a distillation column. The distillate contains 90% A and the bottom stream composition is 95% B. You are supposed to draw and label the block diagram. So first of all, these are distillation column. I said we can use blocks to represent them. And then a distillation column should have just one feed inlet from the question here, and then our two outlets. Our feed was 100 kilogram per hour. So you write your feed on top of your input stream. And then the composition comes beneath it. 50% A and then 50% B. Our distillate is made up of 90% A. Now when you have 90% A, you are just looking at two components, A and B. So when you have 90% A, that means the other one will be what? 10% B, right? Because they should sum up to 100%. They are just mass percent or mole fractions. Sorry, mass fractions. Then our bottoms consist of 95% B, and so the rest will be 5% A. And then we can have our distillate and then our bottoms. Now, the whole idea is that the 100 kg per hour is entering your distillation column, and that 100 kg, it consists of 50% A and 50% B, which we cannot see with our eyes, but then just take this as a pipeline, right? And then there's A and B in the pipeline. So what we can see is this one entering the distillation column. When it enters, it separates it into two. This one comes out, and this also comes out as a pipeline, right? This also comes out as a pipeline. These are what we are calling them as streams. So stream D and stream B, and then this stream, which is 100 kg per hour. And our components are these: the A, the B, the A, and the B. These are our components. And our compositions are the mass percent or the mass fraction: 50%, 50%, 90%, 10%. So when the 100 comes in, it leaves, it separates into two, D and then B. These are also fluids, but then they are unknowns. That's why we're treating them as D and then B. Right? In the normal sense, you are supposed to also get this as something like this, with let's say 80 here and let's say 20 here. Right? So the whole idea of the mass balance is that when I have 100 kg entering something, and then that thing split it into two, right? What is coming out? This D and then this B. When I sum them up, I should get to that 100 kg per hour. That's the whole idea of the mass balance. And one other thing I also talk about is that when it comes to the individual components too, the A and the B, the amount of A present in the feed that is entering, it should be equal to the amount of A which is living in both of them, right? So when I sum the amount of A here, then the amount of A here, it should be equal to the amount of A entering. The material balance is when I have 100 kg per hour of a stream entering into a distillation column and I'm getting two output, then it means that my two output, when I sum them up, I should get my 100 kg per hour. That is the very first approach. And then the other thing you should also take note is that my components which are present in that 100 kg per hour, they won't get lost. They're also coming out. So the ones that are coming out, if I take this stream, the amount of A present in the stream, mind you, this is not an amount of A. This is just a fraction. Just saying that any value you have here, A has 90% of that value, but then we don't know that particular value, right? So when I get this value here and I could multiply it by my 90% here, I'll get the amount of A actually coming out from the D, right? So when I sum the amount of A here and then the amount of A here, it should be equal to the amount of A entering the feed. And then the amount of A entering the feed is 50% times 100. The same applies to the B. The amount of B entering should be equal to the amount of B coming out. So what is entering here should be equal to the B coming out from here plus the B coming out from here. This is the whole idea of the material balance. So this is the diagram we are supposed to draw. The moment you get this diagram wrong, just know that everything is also wrong. So the next example, suppose a stream of 100 kg per hour or brackish water consists of 0.05 weight by weight percent of sodium chloride. Please, this weight by weight percent is just mass fraction. Anytime you hear weight percent, it's mass fraction or mass percent. Right? But then because this is in percentage, it's a mass percent. of sodium chloride and 0.95% of water. A process separates the water into a stream of pure water and brine. Determine the number of stream variables in the process. So first of all, we have our process unit here. We have the question is, suppose a stream of 100 kg consists of this. So these are the compositions, which are 0.05% sodium chloride, 0.95% water of water. A process separates the water into a stream. So it enters the process unit and then it separates them. The moment you hear something is separating two components, just know that we are going to get two outlets or two outstreams that will be coming out. So the process separates the water into a stream of pure water. So that will be one stream, pure water here, and brine, the other stream. From this question, it means that because this is pure water, it means the stream here, the P here, consists of 100% water, right? And then this one is also brine. So here also consists of 100% brine. Flow chart scheme, sometimes you wouldn't be given the feed entry. I mean, the actual fluid of the feed entry. So with that, you can set a basis. You can just assume any basis for the feed entry. But you can choose. Someone might also choose a different fluid of feed. Let's say 200 kilogram per hour. You might end up getting different. You might different answers. But then when it comes to the percent, the answers will be the same. And also, even when you want to talk about the actual fluid, even though they would. So if let's say we weren't giving this feed the 100 kg per hour entry, and then I decided to use 100 kg per hour, I might end up getting my D here to be, let's say, 80. If I'm getting 80 kg per hour and my B as 20, someone who used let's say 200 kg per hour will also get another value here which will be different from the one I have here. But then that value here and then here that the person will be the same scale factor, answers by 2. You end up getting his answers the same thing. Some might also use a different feed here that, let's say, the person might use 5 kg per hour. And the person uses that 5 kg per hour. That means when you multiply a certain number, which to me I don't know, but then when you do the scale factor and you get to that particular number, when you multiply that number by all the person's answers, you end up getting the same answers as yours. But if someone uses, let's say, a different feed flow rate, let's say 25 kg per hour, but then the person gets his answers wrong, you realize that when you multiply that scale factor by all the person's values, you're not going to get the same answers. So that is the whole idea of this flow chart scaling. And you can actually find the scale factor as your new stream amount or your fluid divided by your original stream amount of fluid. So any value that you choose, when you divide by the actual one, you get a certain value, and that will be the scale factor. And for that scale factor, when you multiply through all the values you have, we end up getting the same answers as, if you end up getting different answers. So something like this. Let's say we have N1 and N2. This one we have two inputs and then one output. So something like a mixer here, because you are mixing N1 and then N2 and then you're getting just one output. When someone uses a scale factor of 100, and let's see if you are using 1 here, the person is going to use 100 here, and the person will get 100 as entry coming out. When I multiply this one's own by 100, I end up getting the same thing, 100. So for instance, you can try this example here. A 60-40 mixture by moles of A and B respectively is separated into two fractions. A flow chart of the process is shown here. It is designed to achieve the same separation with a continuous feed of 1,250 pound moles per hour. Scale the following chart accordingly. So let's say you have a question, and then the first question has 60 to 40 by moles. So we have 60 to 40 mixture by moles. This means that the moles of A, this are talking about the actual moles, not mole fraction. The moles of A is 60 moles, and then out of B is 40 moles. and then these two come together to form the feed. When you sum them up, we get 100 moles. So you have 100 moles entering the separator. It's separated into two fractions, so upstream and then the downstream. It is designed to achieve the same separation with a continuous feed of 1250. So let's say our first problem is we having 100 moles of both A and B as a mixture, and then it enters the separator. And then let's say we've done our balances and everything, we've gotten our answers. And then we had the one coming out here, which is our distillate here, to be 50 moles. And then the one coming down here, I think you have to sum the two. You also get 50 moles. Right? Now, when we change our question, now we change our feed from 100 moles to 1250 pound moles. The moment you change your feed like that, you're not supposed to restart your calculations again. What you're trying to say is that you just have to go and find your scale factor, which will be your new value here. You're talking about your new stream amount divided by your original one. So 1250 divided by your original one, it was 100. You get 12.5. You just have to multiply the 12.5 by all the stream values you had in your previous calculation. And then you will get the actual answers when you use your 1250 to solve your calculation. Okay, so that's the whole idea of the flowchart scale. So this is it. So let's say we first solved our question based on this 100 moles and then we had these values. Now when we change our feed to 1250 and the compositions are still the same, like 60%, 40%, then we don't have to start the overall mass balance again, do the calculations and everything again. Just have to find your scale factor, and after you just multiply them by what you have here and then what you have here. Please, you don't multiply them by the fluids or the you don't multiply them by the mass fractions and then the mole fractions. For that one, they are fixed, they're always the same. If you multiply by that, you will get this, and that will be your final answer. This is one of the most interesting parts when it comes to material balance calculations. Your degree of freedom analysis. Now, when you are trying to solve a material balance problem, there are some questions you need to ask yourself. How many questions or how many equations do you need? And where are you going to get those equations from? Of course, you get those equations from your material balances, but then you should know how many equations you need. And then, mind you, even from algebra, I realize that when you go to the matrices part, you guys are doing something like sometimes your equation becomes unsolvable. You end up getting infinitely many solutions and all that. So you should know whether the question given to you is solvable or not. Otherwise, you might end up solving and solving and solving and solving. You wouldn't finish. Right? So to determine whether your problem given to you, the problem given to you is solvable or not, you need to perform the degree of freedom analysis. And when you do that, that will naturally help you to know whether your this one is solvable or not. I don't know. I think it's somehow related to the rank and things you did in the matrices. If your rank and then your distance are not the same, then it means your problem is unsolvable, something like that. So when you perform your degree of freedom analysis and you get zero, then it means it is solvable. You are going to get a unique solution. Now let's come to how to actually solve for the degree of freedom analysis. To solve for the degree of freedom analysis, you first need to draw. You should be able to draw a description given to you. Label all the unknowns and then the knowns before you can start your degree of freedom analysis. Right. The equation is the degree of freedom analysis is equal to the number of unknown variables you have minus number of independent equations. And also we can also add yes. So your degree of freedom analysis, your degree of freedom is number of unknown variables minus number of independent equations. We can also subtract other relevant equations we have too, but then they are all embedded in the number of independent equations. Right. We are using independent equations here because you might end up getting some of the equations being interlinked, or you can find some of the equations embedded in other equations. For instance, when I have these two equations here, how do I know that these equations are all dependent or independent? The first equation is x plus y equals 3. And then our second equation is 2x plus 3y equals 6. our third equation is 3x plus 4y equals 9. Now, when I sum equation 1 and then equation 2, I will end up getting 3x plus 4y equals 9, which becomes my equation 3. So it means that equation 3 depends on equation 1 and 2. Right? And then when I subtract equation 1 from equation 3, I'm going to get equation 2. So it also means that equation 1 also depends on equation 2 and 3. When I also subtract equation 2 from 3, I end up getting equation 1, which means that my equation 2 also depends on 1 and 3. You realize that out of these three equations, there are only two of them that are independent. And that two of them could be any of them. You can just select any of the two. So you can either select equation 2 and then equation 3, or equation 1 and 2 or 1 and 3. And then we count them as your number of independent equations. So in a case like this, if you want to find the degree of freedom, we have a number of unknown variables. So what to be our unknown variables here? 1, 2. There are only two unknown variables. And then our number of independent equations are 2, because 1 depends on 2. So now when you get 0, it means that your degree of freedom is 0, and hence the problem is solvable. And we are going to get you. What if after summing these two, like our third equation was also an independent equation on its own, or let's say all the three equations were independent, then it means that I will now be 3. When I subtract, I'm going to get negative 1 as my degree of freedom. What it means is that my values that I've gotten, when I solve this equation, I'm going to get a unique answer. So if someone person will get, it will be different from when someone solves equation 2 and 3 together. You'll get different answers. Freedom is enable you know whether the problem you have is solvable or not. And then the relation is your number of unknown variables minus your number of independent equations. Now, I was saying that with the independent equations, you should make sure that all the equations you are going to look at are independent. Some don't depend on the others. But then when you look at these three equations here, equation 3 depends on equation 1 and 2, in the sense that when I add equation 1 and equation 2, I get equation 3. Right? So that means equation 3 depends on equation 1 and 2. The same applies when I subtract equation 1 from equation 3, I will get equation 2. So it means that now equation 2 depends on both equation 1 and equation 3. So out of these equations, there are only two of them that are independent, like they stand on their own. But then we can't actually know the exact ones that stand on their own. What we can do is that we can just take out one of the equations, any of them, and then we can see that only two of them are independent. For instance, when I have equation 1 and equation 2 alone, there is no way I can say one depends on 2. No. Also, when I have equation 2 and 3 standing alone, there's no way I can say 2 and 3 are dependent. Right? Exactly. But then you can also take note of something here. You can have one equation, let's say x plus y equals 3 as one equation. And then my other equation will be 2x plus 2y equals 6. In a case like that, the equation 1 and that equation I'm talking about, they are dependent. Now let's come back to our material balance. For most non-reactive systems, the number of independent equations is equal to the number of chemical compounds present. Please take note of this particular information. For most non-reactive systems, the number of independent equations is equal to the number of chemical compounds present. Now, the chemical compounds present here we are talking about is the number of components we are looking at. So when I take a question like this, if I want to perform the degree of freedom analysis here, my number of independent equations will be equal to the number of components present. And what are the number of components present? The number of components present are just A and B, two of them. And please, the number of components present, we take it from the inputs, not the output streams. So my number of independent equations will be 2. And I had them from this. If you want to solve them manually, it means that in actual sense, when you are doing a material balance, you first have to do overall balance, which will be 100 equals D plus B. That will be your first equation. Your second equation will be, now we come to the component balance. You have to do balance for each of the components. So 50%, which is 0.5 times 100 is actually the amount of A present in the feed, and that should be equal to my D here times 0.9 plus my B here times 0.05. That will be my second equation. And my third equation will be 0.5 times 100, which is for the B, to be equal to 0.1 times D plus 0.95 times B. And that will be my third equation. Now you realize that when you sum the last two equations I talked about, you will get your first equation, which is your overall mass balance. So it means that you'll be having, even though you'll be having three equations, only two of them will be independent. That's why it's a general rule that for most non-reactive systems, the number of independent equations is equal to the number of components present. And then for most, we'll talk about the reactive systems tomorrow. And then today we are looking at non-reactive systems. When your degree of freedom is zero, it means that the system is completely defined. You get a unique solution, or simply the problem can be solved. Now, when your degree of freedom is greater than zero, the system is undefined or underspecified. That means you have less number of equations. And when you still want to go ahead and solve that, you're going to get infinite number of solutions. When your degree of freedom is less than zero, that means when it is negative, that means your system is overspecified or overdefined. And you might end up getting, you will get more equations than the variables, and then you wouldn't be able to solve, because based on the equation that you select to solve, you get different answers for each of them. Now let's look at this question. Feed contains 36%. Feed contains benzene, which is 36%, and the remainder is toluene. Overhead contains 52% B. Bottoms are to contain 5% B. Draw the degree of freedom table and comment on the solution. We have our feed, which consists of 36% benzene, and the remainder is toluene. So to do our diagram, this is our process where we are going to do the separation. Or this is our process unit. You don't know what's actually going on. And then they are talking about our feed entering, and then our overhead, and then our bottoms. And then our feed enters, which is this. It consists of, now these are our two outputs. Our overhead here, then our bottom is here. Our feed consists of, okay, so we are labeling this as our feed, F, right? Because we weren't given the actual value, so F here. Let me call this A1 for the toluene, because you don't know the actual value. But then we can find it from subtracting 36 from 100, right? And then this are B, 36%. You can as well write your answer straight away, your A1, because definitely your A1 will be 64. You can just write 64, toluene T, right? And I'm just writing here as A1. And then these are distillates, or our overhead. I'm representing the flow rate of the overhead as D. And then this is our bottoms. I'm representing it as W. Now, our distillate or our overhead consists of 52% B. And then our bottoms consist of 5% B. We don't know our A2 and then our A3. Our A2 here is now our toluene in the distillate. Our A3 here is our toluene in the bottoms. Now, when we want to perform the degree of freedom analysis, now our A1, A2, and A3 are unknown, but then we can find them, because you know when you sum this and this up, you get 100. So A1 will just be 64. So we know A1 now. We know A2, which will be 48. So we now know A2. Our A3 will be 95%. So A2, A3, A1, they are all known. So then left, the remaining unknown variables are F, W, and then D. So there are three independent variables here. But the number of stream variables here are 6, which are F, A1, W, A3, A2, and then D. But then when we want to talk about the number of independent variables, because A1 depends on the value of B, right? If I know B, I'll know A1. If I know B here, I'll know A2. If I know this one, I'll know A3. So when you want the number of independent variables, they are going to be three. Going to be your F, your D, and then your W. And your number of independent equations, because this is non-reactive system, our number of independent equations will be the number of components that we have, and they are two, B and A, which is benzene and toluene. So two components. So our number of independent equations are two. Now when we want to find the degree of freedom, it will be your number of variables, 3 minus 2, and that will give you 1. Now someone might also solve it in a way that the person will assume that he or she doesn't know the value of A, the value of A3, the value of A2. So in a case like that, you are going to have 1, 2, 3, 4, 5, 6, 6 number of variables. And then your number of equations, your number of independent equations will now be 2, because you have only two components here. So 6 minus 2. Right. Now we can come to, see, I was talking about other useful informations you have. You know mass fraction or mass percent supposed to be 100 when you sum them up. So we can have another equation which will be B plus A1 should be equal to 100. And that also counts as one equation. You can have another equation which will be B plus A2 should be equal to 100. That will be your second equation. You can have another equation which will be B plus A3 equal to 100. And that will be your third equation. So when you sum them or you add it to the two independent equations you have here, you get 5. And then your degree of freedom becomes 6 minus 5. And you still end up getting 1. For the degree of freedom, the number of variables, the number of independent equations we are working with matter. What matters is you degree of freedom for it. So someone might also solve this in a way that you'll be getting that 6 minus 5 as your degree of freedom analysis. And then you final answer. What matters most is you getting the 0. That means you are trying to say that the question is solvable, you get unique answers, which is not true. For mass percent, this should sum up to 100. So if this is 36%, our feed consists of 36% B, and then our remainder is toluene. So if our remainder is toluene, that means our toluene will consist of 64%. Yes, so 64% of toluene. That's our A1 here. But then I decided to label this as A1, right? So in actual sense, our A1 here is 64% of toluene. Our A2 here will now be 100 minus 52. That will give us 48. So we know this, we know this. Our 5% here, when you sum it to this, you should get 100. So our A3 will also be 95%. So our actual number of unknowns that we don't know are F, D, and W. So that is 3 unknowns or unknown variables. When it comes to the number of independent equations, now we're saying that for the number of independent equations for non-reactive systems, the number of independent equations is equal to the number of components present. And our components present in the field are just 2, 1 and 2. So 2 independent equations. When you subtract them, you get 1. And I was saying that someone might also solve the degree of freedom analysis in a way that the person will assume not to know the A1, A2, and then A3. So the person's number of unknowns will now be 1, 2, 3, 4, 5, and then 6. The person will now have 6 number of unknowns. When it comes to the number of equations, we have 2 independent equations from the component balance, or let's say from the component, number of component present. You have 2 equations here. Now when it comes to mass percent too, we can derive other equations. We can say that 36 plus A1 should be equal to 100, and that will also be another independent equation on its own. Adding up to the 2, making 3. And then the person will have to add this one also. 82 plus 52 should be equal to 100. And that's also another independent equation on its own. Adding up to that, we're making 4. And then the person can also add these two. 5 plus A3 should give you 100. And that will also be another equation on its own, making 5. So we end up getting 5 number of independent equations. And then your number of variables are 6. So when you subtract, you get 1. The person who actually wrote the final answers 64%, 48%, and then the 95% wouldn't count this as unknowns again because you now know them, right? The person is only going to count your F, your D, and then your W as your number of unknown variables. So you just get 3. And then when you add your components, number of components as your independent equations, which are 2, when you subtract, you get 1. And I was trying to say that you writing 3 minus 2 giving you 1 or 6 minus 5 giving you 1 doesn't really matter. What matters is you getting the degree of freedom final value correct. So if you are writing, probably someone might also solve in a way that the person will write here as 64, but then leave here and here as unknowns. So in such case, the person will have 1, 2, 3, 4, 5, 5 unknowns. And then the number of equations will be the 2 from this plus this 3 plus this 4. And then the person will write 5 minus 4. The person will get 1. You wouldn't be marked wrong for that. The fact that you are getting the 1 as your final answer is what matters. You can also try this question. We have humid air entering, and these are the flow rates O2, N2, H2. We don't know them, so N0, N1, N2. We also don't know what the amounts at which they are coming out. So N4, N5, N6 are also unknown. We don't know N3 too. We don't know N3. So our number of unknowns are 7, which are 1, 2, 3, 4, 5, 6, 7. So 7 unknowns. And then to get the number of independent material balance equation, they are based on the number of components present. And the components are 1, 2, 3. So you have 3 independent equations. Now let's see if you have any other relevant equations. We can have this equation here. You've been given volumetric flow rate. We know density of water to be 1,000. When you multiply the two, we can get a value here for your N3. So that becomes another relevant equation. Adding up to the 3, getting we 4 equations. So adding up to your 3 equations, and then we end up getting 4 equations. We also have another equation here, which is 95% of inlet water. So our water that we have here, which is coming out from the condenser, consists of 95% of our inlet water here. So there's actually a relation between these two. This one coming out and then this one entering. There's a relation between them, 95% of that. That's also another relevant equation. Now, because you are looking at humid air, we can say that when you take air, we know the ratio or the proportion between our nitrogen and then our oxygen. So when you know the relationship between, we know the proportion of our nitrogen and our oxygen. That is just another relevant information that we have. And then we can also add it to that. When we add it to that, you are going to get 6 equations. So one from the ratio or the proportion of nitrogen and then oxygen. Right. We have 7 number of unknowns. Yes. And then our water that is coming out. Now trying to see that 95, this water that is coming out is equal to 95% of our inlet water that is entering. So that becomes another equation. So we can write N3 is equal to 0.95 times N2, which is also another relevant equation, but then it is also independent. When you add it to the 3 equations that we get from the component part, we get 4 equations. And then we also have flow rate of water given here. Now, when you know the flow rate of water, you also know the density of water. And then we know how to relate density and flow rate. This is volumetric flow rate. Density is equal to mass flow rate over volumetric flow rate. So when you multiply them, we can get the mass flow rate of water, N3. So N3 can also be written as this times the density of water, which is another relevant equation. but then it's also independent. When you add it to the four that we have, we get five equations now. And also, our humid air that is entering, because it is air, we know the compositions or the proportions of nitrogen and oxygen present in the air. So you can see, even though these ones are the actual fluids, we don't know the actual fluid, but then we know the fractions, that the ratio of nitrogen to oxygen is around, let's say, 79 to 21%. Right? So when you know that, that's just another relevant equation we can add up to the five that we have, and then we get six equations in all. When you subtract it from the seven, we end up getting the degree of freedom to be one. That means the problem is unsolvable. This is it. Okay. So let's try one material balance problem. 1,000 kg per hour of a mixture of benzene and toluene containing 35% B. So our feed here consists of just benzene and then toluene, which are 35% benzene, 65% toluene. Even though when given the 65%, we know percentage of the benzene plus that of the toluene should give us 100. So when we know the benzene, we subtract from 100, we get the toluene. And our feed is 1,000 kg per hour. It enters the process unit, and then we get two outputs, our top stream and then our downstream. The mass flow rate of the top stream is 380 kg B per hour. They've given us the mass flow rate of the top stream, but then this mass flow rate was in terms of benzene. So they gave us the benzene's mass flow rate rather, right? Which is 300 and sorry, okay, I think this is a mistake. It's supposed to be 380 kilogram per hour. The B was not so 80 kilogram per hour. So that becomes our top stream. And then our top stream contains 90% B. Right? So 90% of B is our top stream. Then will be 10%. But it should sum up to 100%. So that would be 10%. Stream, we aren't given any information on the bottom stream, also consists of benzene and then toluene too, but then we don't know. The question is asking us to write balances on benzene and toluene to calculate the unknown component of. First of all, you have to go with our overall material balance or overall mass balance. The overall mass balance is you looking at the total will be our first equation, which will be overall material balance. Then we can come to our component, our benzene and our toluene. Remember, I said that to find our actual flow rate of benzene, you should take note that this percentage here are mass percent or mass fractions. So to find the mass flow rate of benzene, you just have to multiply your 35% by your 1,000. In another sense, 0.35 times your 1,000. And that should be equal to your benzene here is 0.9. So mass fraction is 0.9 times your 380. This 380 here is the flow rate of the top stream, like everything combined, both the benzene and toluene flowing at the top stream. We don't know that from the bottom stream, so we can actually put any variable there as our mass percent for the benzene in the bottom stream, and then we need to multiply it by the actual flow rate of the bottom stream, which is W. Right? So for the benzene balance, we get our benzene balance will be our F, which is our feed entering, times our mass fraction of benzene in the feed. So that this F here is mass fraction of benzene in the feed, and that should be equal to our distillate, which is our flow rate of our distillate, times our mass fraction of benzene in our distillate, right, plus our mass flow rate of W times mass fraction of benzene in the bottoms. When you sum them up, this is what you should get. So that becomes your component balance for the benzene. We do same for the toluene. Our F, which is our feed, times our mass fraction of toluene in the feed should be equal to our distillate fluid times mass fraction of toluene in the distillate plus bottoms fluid times our mass fraction of toluene in the bottoms. Now we realize that you have three different equations. So when you want to perform your degree of freedom analysis, the degree of freedom analysis is saying that to get the number of independent material balance equations, that should be equal to the number of components you have. Then these are number of components, 2. So independent number of equations are 2. To understand it properly, even though you have 3 equations, now when you sum equation 2 and 3, what do we get? We will get fxbf plus fxtf. You can factorize f out here from this portion and add these two. When I factorize the 2 out, when I factorize f out, I will get xbf plus xtf. And then because they are mass fractions, they will sum up to 1. So that gives me f. And that should be equal to, here too, I can factorize the d out. My xb and my xt here will also give me 1. So I end up getting f equals to d plus w when I add these two. This means that this equation depends on these two. That's why it's fixed that the number of independent equations for your material balance will always be equal to the number of components that you have. That is for non-reactive. Now, from equation 1, we know our feed to be 1000 kilogram per hour, and then our top stream, which is D, is 380. So we can find our W from here. Our F should be equal to D plus W. That's why in our previous slides, I was like, in one of our slides, I was saying that it's best to start with your total or overall material balance equation. This is overall material balance equation. So my F is 1000, and then my D was 380. When I subtract, I can get my W, and that would be 620 kilogram per hour. Now, since I have my W, I can put it in any of the equations here. I know F, I know XB, I know D, I know XBD. They gave it as 90%. And now I know my W, but I don't know my XB here. So I can use that to find my XB. The same way, I know my F, I know my XT, I know my D, I know my XT. They gave XB to be 90%. So my XT here will be 10%. So 10%, which is 0.1, plus I now know my W from here, and then I can find my XTW. When you do that, you will get, so when you are putting in the equations, so from equation 2, this, my F is 1000 times my XBF was 35%. So in terms of mass fraction, 0.35. And that should be equal to my D distillate was given as 380 times mass fraction of the benzene in the distillate was 0.9, which is 90%, plus my W here is 620 times my XBW, mass fraction of W in the bottoms, it wasn't given. So when I get that, when I solve this equation, I get XB to be this. I don't need to put in the values again to go and solve for XT. I can just write XT is equal to 1 minus XB here. And then I'll get my XT here. So just 1 minus that, then I'll get this. I'll send you the slides and then you try this question too. These are the answers you should get. An aqueous solution of sodium hydroxide contains 20% sodium hydroxide by mass. It is desired to produce an 8% sodium hydroxide solution by diluting a stream of the 20% solution with a stream of pure water. So now let's take note. This is our process unit. And then the first part of the question is an aqueous solution of sodium hydroxide. Now, because it is aqueous, the moment they give you the composition or the amount of sodium hydroxide present, the remaining becomes water. If it contains 20% sodium hydroxide, then the 80% is water because it's an aqueous solution of sodium hydroxide. It is designed to produce an 8% sodium hydroxide solution. That means we are diluting it. They know how to dilute. When you are diluting, we add water, and then the water we are adding is supposed to be a pure water. So we feed in our water here, and then what comes out to be what we are producing. So we are producing 8% sodium hydroxide. And the moment we produce 8% sodium hydroxide, it means the rest is still water. The water emptying here is 100% water. And then you can solve. So when you solve, these are the answers you're supposed to get. You perform your material balance. 100 should be equal to M2 plus M1. Then you can do balance on the water. 100 times 0.8 should be equal to M2 times 0.92 plus your M1 times 1 because the water is 100% here. And then you can do your balance on the sodium dioxide too. And then when you solve, you should get these answers. So you guys should go and try out this question. I'll send you the slides as soon as possible. Try out this and then try out this one too.